So the goal of this week is to talk about some of the quantum information technologies that are not quantum computing. So the rest of the course after this week is going to be kind of with an eye towards thinking about quantum computing. But I thought it would be really interesting to spend some time talking about sensing and communication, because in many ways, those are technologies that are already here. And maybe in some cases have been here for decades. So it's a nice place to start. All right. So the three main quantum technologies that kind of form the foundation of this field of quantum information science and engineering are quantum computing, and that's the subject of most of the class. And if we had to define quantum computing, we would say it was applying quantum mechanics to perform computations. There's kind of a subgenre of quantum computing called quantum simulation, and that's using quantum principles to improve modeling and simulations. A lot of times, we need a way to simulate quantum computing before quantum computing really exists, and that's kind of in that subgenre. So there's quantum computing and there's quantum simulation. And then there's quantum sensing, which, as I mentioned, is a technology which we're going to talk a lot about today that's already sort of here. And this is using quantum systems for high precision measurements. And then finally, we have quantum communication. And this is transporting or exchanging quantum encoded information. All right. So if you look at this graphic from NIST, they kind of show a roadmap of the difficulty of a quantum problem and the sort of time horizon to its realization. And they categorize things like quantum measurement, quantum sensing, and quantum key distribution, which we'll all talk about today, as the known. We already sort of know how to do this. And practical commercial applications of this are sort of in the now to a few years out time horizon. There's also, if you go up in complexity, there's sort of things that maybe unlikely or impossible, and they put quantum computation there, which I think is kind of interesting. But that's still it's expected, but it's very hard. There's also things that are sort of in the middle ground, quantum widgets. We'll talk about things like quantum repeaters today. That's in that category, I would say. And then things we really haven't even thought about, like maybe quantum engineered photovoltaics or something like that. All right, so when we think about quantum sensing, quantum sensors really exploit the fundamental properties of atoms and light to make measurements of the world. So what's interesting about using the quantum states of either particles or light is that they're extremely sensitive to the environment, and this is exactly what makes them challenging to use for quantum computing, right? This sort of coherence issue is tricky for taking multiple qubits or quantum states and coupling them together. But in a sensor, often you only need one, and you're just going to kind of look at perturbations based on how it interacts with the environment. So that sort of loss of your excited state, for example, can be the tool to do the sensing. So it's kind of a much simpler idea. And so quantum sensors can be envisioned to do things like quantify acceleration, measure magnetic fields, measure rotations, gravity, and even the passage of time. And you can see a collection of different potential applications or current applications shown here. So in biology, there's things like measuring neural signals in the brain or measuring heart behaviors. Lots of applications in spectroscopy, and we'll talk about a couple today. There's also like high precision navigation, GPS types of technologies. There's things that are sort of a more practical importance for engineering, like surveying. And there's kind of things that could be really important for solving some of the big energy challenges, like monitoring and measuring CO2 emissions. And there's also applications in very fundamental science, and we'll talk about a little bit of that today too. So if we look at the quantum sensing platforms, they look a lot like the platforms that we will consider for qubit technologies in quantum computation. So we have things like neutral atoms, And the qubit description, the thing that's going to do our sensing, is thinking about changes to the energy level of an electron in a laser-cooled atom or a warm vapor of atoms. And this transition between energy levels can allow us to measure things like magnetic field, rotations, and things like that. And there's already prototypes of that type. There's also trapped ions. And here we're using the internal energy levels of ions trapped in electromagnetic fields. And these can be used to measure things like time and electric fields. And there's plenty of theoretical evidence that this is possible. Photonics is a big one. So using two modes of a photon, this can in principle be used to measure things like temperature and position. And there's many proof of concepts out there in this realm. Spin qubits of various kinds, including NV centers, for example, use the spin of an electron localized on a defect, for example, to measure things like magnetic field, electric field, temperature, pressure, rotation, many proof of concept applications, and even some practical applications beginning to emerge. And then the biggest kind of area where there's already many practical applications is in the context of superconducting circuits. So if we look at differences in Cooper pairs between islands of superconductor, we'll talk a lot about this today, we can use that to measure magnetic fields and electric fields. And it says prototype, but I mean, we can buy a SQUID, and we'll talk about that today. And elementary particles, we can use free electrons to measure magnetic fields and photon densities and gravity, and there's proof of concept in that category as well. All right, so let's talk about some existing technologies. So we can kind of classify current sensing technologies in two buckets. The things that already exist, and the two that we're going to really focus on today are atomic clocks and SQUID magnetometers. And then there's the kind of current to next generation technologies like NV centers. So atomic clocks. So since 1968, the International Standards System has defined the second as 9,192,631,770 cycles of radiation corresponding to the transition between two energy levels of the ground state of a cesium-133 atom. Did you know that that's how we define the second? I see some nods. Maybe some people did, maybe some people did not. So it used to be that we measured the second based on the Earth's orbit. And maybe that's the kind of what you expected us to use as a measure of time. But it's not. This is way more stable than the Earth's orbit. And so this is how we actually measure time today. So how does this work? So if we think about a cesium atom, we have the nucleus, the 133 cesium nucleus, and we have the outer 6s valence electron. And if we think about the energy state of this valence electron, so here's our 6s electron, it's going to be split by fine structure that arises from a magnetic interaction between the electron spin and the big nuclear spin that's created by this really heavy cesium-133, the orbital angular momentum of that nucleus. So we have this fine structure splitting. And the thing that determines the fine structure splitting, so the reason that there's an energy difference here, is because, let's say in the ground state of the lower energy of our fine structure splitting, we have the electron spin and the nuclear spin aligned anti-parallel. And in the upper branch, we have the nuclear spin and the electron spin aligned parallel. So they're it is sort of easy to imagine that these two interactions would have different energies, right? There'd be either additive or subtractive. So the fun thing about this is that this fine structure splitting is really, really tiny. So delta E here is, I don't think I have it written anywhere, very small. It's 0.00038 electron volts, tiny. And so it's this cycling of energy between these two states that we use to measure time these days. The exceptional precision of the tiny energy splitting is what allows us to measure time with the precision of 1 second in 1.4 million years. So pretty remarkable. Cesium isn't the only atom that people make clocks with. You can do it with many other heavy atoms. And it's really this heavy atom effect that the distance between that outer valence electron and the nucleus is really humongous on an atomic scale. So you can kind of see in the bottom of this image, the radius of the nucleus is 6.1 Fermis, and the radius of the atom is 55,000 times bigger than that. So on a particle level, these things are really far apart. So these atomic clocks operate in the optical frequency domain, and they have approached and are expected to exceed a frequency uncertainty of 1 part in 1 times 10 to the 18th. And so they can be used, obviously, as precision sensors in addition. So the sensitivity to the fundamental physics constants, for example, has been explored for detection of dark matter and time variations in those fundamental constants. So this is a pretty neat technology, and it's pretty old at this point. All right, so these like little energy splittings are things that are going to come up a lot as we talk about qubit technologies. And when we talk about quantum computation, it's going to be we need ways to kind of initiate the qubits and read them out. And so thinking about those energy splittings and which kind of sizes of energy splittings are going to be useful for us is going to be a big thing. All right, so the other major existing quantum sensing technology is called a superconducting quantum interference device, or a SQUID. So this is a very sensitive magnetometer that's used to measure extremely weak magnetic fields, and it's based on superconducting loops containing something called a Josephson junction, which we'll talk more about because it's very important to understanding superconducting qubits in general. And so these SQUIDs are sensitive enough to measure magnetic fields as low as 5 times 10 to the minus 14th Tesla. And measuring fields that low typically require a couple days of average measurements. But to kind of put that into perspective, I kind of have the scale here of what some common magnetic field strengths are. So the Earth's magnetic field is around 10 to the minus 4 Teslas. So it's pretty big by comparison. The human heart has a magnetic field that's about 10 to the minus 10. And muscle impulses create a magnetic field that's like 10 to the minus 12. So those are all orders of magnitude larger than the sensitivity of a SQUID, which is crazy. And so one thing that you'll have to keep in mind as you think about how a SQUID works is we need a way to isolate all of that stuff from the SQUID for it to do its job. All right, so the DC SQUID was actually first invented in 1964 at Ford Labs, so the car company. And this was shortly after Brian Josephson postulated the Josephson effect, and folks at Bell Labs in 1963 first created a Josephson junction. So let's see, what is this Josephson stuff? So the Josephson effect is a manifestation of long-range quantum coherence of superconductors. So the simplified picture is shown here. So I have 2 regions of superconductor, and they're put pretty close to one another. And I have a quantum mechanical phase measured in each of these superconductors, and I can label them as phi 1 and phi 2. And in an ordinary material, the phases of these 2 different spots in my material are going to be unrelated. But in a single piece of superconductor, the phases of the 2 different spots would have some specific relationship related to the property of the material itself. So in this situation that I have in this drawing, if the 2 regions of superconductor are close enough together, even though I have this little barrier region between them, their phases are going to be related. And this isn't quite a manifestation of entanglement, but this is a manifestation, this is a quantum coherence. And so functionally speaking, electrical currents can flow between these two regions of superconductor with basically zero resistance. And that current that flows between the two is called a Josephson current. All right, so these Josephson junctions generally have a much lower critical current. That's the maximum current that can be carried before resistance begins to appear than the two superconducting pieces themselves. And that's kind of the unique thing about the junction. So these Josephson junctions are the active devices of all superconducting electronics, including superconducting qubits. And just like the transistor is kind of the essential active device in semiconductor electronics, this is kind of our fundamental unit in superconducting technologies. And people have built Josephson circuits with up to 1 million Josephson junctions. So the SQUID is a very simple Josephson circuit. It only involves 2 Josephson junctions. So in a SQUID, we have 2 Josephson junctions. Those are kind of in the shaded regions here. And they're connected in parallel in a closed superconducting loop. And the fundamental property of superconducting loops is that they enclose magnetic flux in only multiples of a universal constant called the magnetic flux quantum. And the magnetic flux quantum is very, very small. So therefore can be used to produce these extremely sensitive magnetic field sensors. So the magnetic flux quantum is 2 times 10 to the minus 15 Webers, which are volt seconds. So I'll just write volt seconds. And so I just sort of showed you kind of scale on the last slide. So this is, very, very small number. And the small fraction of the Earth's field that is not attenuated by the magnetic shielding in the SQUID magnetometer is something that needs to be carefully considered. So there's a lot of fancy electronics that are kind of built into the SQUID to make this all work. And so you can kind of model, how much magnetic field you're going to be inevitably experiencing from the environment based on properties of your shield, et cetera, et cetera. And so you can correct for those things. But those things have to be known very precisely. So in addition to sort of external noise, like the Earth's magnetic field, the SQUID sensitivity is also limited by the intrinsic noise in the device, which is in a 4.2 Kelvin niobium SQUID, which is kind of the typical instrument. It's typically about 1/millionth of a flux quantum. So the internal noise in a 4.2 Kelvin niobium SQUID is about 1 in 10 to the 6th, that's 1 million, of the flux quantum. So it's pretty small, which is nice. All right, so there's some inherent periodicity to the SQUID because it measures things in flux quanta and not in sort of an absolute scale. And you can do some electronic manipulation to get around that, but often we're just measuring things in a SQUID relative to some known standard. So it doesn't need all that fanciness. So if you look at some data taken on a SQUID magnetometer, it might look something like this. So I have temperature plotted on the x-axis here, and this is data taken at a magnetic field of 1,000 Oersted. And I'm measuring something called the magnetic susceptibility. And this is a measurement that's done a lot on paramagnetic molecules, for example. So if you have ever worked in an inorganic chemistry lab and made some transition metal complex that has unpaired electrons, this is definitely a type of measurement you'll want to make. Lots of people in our department do this kind of measurement. And it's also done on similar kinds of materials with unpaired electron density. So this is a vanadium complex. It has vanadium in a tren environment. This is this tetrachelating nitrogen ligand that's kind of a basket on the bottom here. And then it has a nitrile sitting on top of it. And it's vanadium in the 3+ oxidation state, and it has 2 d electrons, which you can kind of see represented in this energy level diagram. So in this energy level diagram, it has lots of interesting things. So I can excite this complex using some kind of light, visible light. It excites, that's the blue line, and it excites from the ground state triplet, which is shown here, to an excited state triplet, and then it undergoes intersystem crossing. So that's movement between excited states with different spin. So it moves to a singlet spin, and then it emits light from that excited singlet state. And so the energy, electron configuration of the excited state's there. And what's fun is that this piece right here, so you see the 0 state and the 1 state, this part of the molecule's fine structure can actually operate as a qubit. So this paper is all about designing a cool molecular qubit. And this fine structure splitting is nearly the identical picture that you get in something like an NV- center. So let's just walk through it for a second. So I have this D2 electron configuration. So 2 electrons in my system. And so as you see right here, this is an S equals 1. So I have 2 unpaired electrons. And there's 3 ways that I could draw 2 electrons in 2 orbitals. So I can draw them both spin up, or I can draw them both spin down, or I can draw them 1 spin up and 1 spin down. So little m sub s is equal to 1, little m sub s equals to -1, or little m sub s equals to 0. Those are my 3 possible spin states. And zero field splitting, in the absence of a magnetic field, allows you to differentiate between those states. So the little m sub s equals +1 and the little m sub s equals -1 are a little bit higher in energy than the little m sub s equals 0 state. Okay, so that's this guy. And so that state, that set of, or what's really 3 states, but it's kind of functionally operating as 2 states, can be a qubit. And D here is the 0 field splitting. And if you are a molecular qubit person, you think a lot about how you can tune the properties of the molecule to change that energy, that 0 field splitting. So how does this relate to this picture? All right, so I'm measuring the magnetic susceptibility of this molecule. So I'm trying to learn something about how the electron density is paired or unpaired as a function of temperature. And so at high temperatures, I'm measuring some magnetic susceptibility. It's 1, so I have unpaired electron density. And then as I go to lower temperatures, my magnetic susceptibility goes down. And so that's telling you about the spins pairing, because you're losing that sensitivity to the magnetic field. All right, so this picture, I kind of spent a little bit of time on it because it's sort of exactly the thing that we're going to hear a lot about when we think about nitrogen vacancy centers in diamond. So the kind of future of quantum sensing is based on this nitrogen vacancy center. So you're going to read a really nice article about this. But color centers in general are fluorescent defects in a lattice. And so generally when we think of a color center, we take some usually wide band gap material. So we'll call this the valence band and this the conduction band. Here's an energy scale. And I can embed one defect or a cluster of defects, and that can introduce new states within the gap. So here's my filled orbitals. Conduction bands my unfilled orbitals. So normally, this is a diamond. The band gap of diamond is like 5.5 electron volts or something, so it's not very useful for anything. Just looking pretty. But I can embed a defect in there and install a pair of energy levels that allow me to do some fun things. So all of the colored diamonds that you may have seen in real life or in pictures come from different defects being in the diamond lattice. And there's hundreds or even thousands of different defects that have been identified to date in diamonds. And as the importance of this platform in quantum information has become more evident, people are trying to discover even more. So there's lots of theoretical defects, and people are just figuring out how to make them. So the main defect that we think about when we think about defects in diamond and quantum information is shown here. So this is the NV center. And I'm not going to spend a lot of time talking about it today, but I'll just kind of lay a little bit of the foundation. So as drawn here, this blue atom is the nitrogen. And the yellow is kind of my vacancy. So that's the absence of a carbon, and all the gray is carbon. And as it's drawn here, it's implying that I've added a nitrogen, I have a vacancy, not a vanadium. I have a vacancy, and the overall charge on this complex, this nitrogen vacancy complex, is 0. So I'm missing a carbon. I've replaced a carbon with a nitrogen, and nitrogen is in group 5 of the periodic table, and carbon is in group 4 of the periodic table, so I've added one more electron. But overall, that system is neutral because I'm missing a carbon. Is that pretty clear? Okay. So that system, NV0, right, I just said, has one unpaired electron. And that's not useful in quantum information at all. It's useful as an emitter. So if you just want to make a pretty color or make it glow, like that's okay. But for quantum information, we need a triplet, just like we just saw in the vanadium example. So what we do is we apply a potential to shift the Fermi level of our nitrogen vacancy center so that it captures an electron. And that's what makes the very special NV minus center, which is an S equals 1, 2 unpaired electrons, ground state. And it has the exact same kind of fun situation that I just laid out in the vanadium example. So it has little m sub s equals 0 ground state, and it has a pair of little m sub s equals plus minus 1 excited states. And in diamond, this energy is in the microwaves. So I can kind of probe or even pump transitions here using microwaves. But normally, just like in the vanadium example, I excite the system using light. I'm not kind of using this little energy to excite the system. I use higher energy light, and then I get kind of natural relaxation processes that populate the state. There's some interesting chemical description of the NV center that describes the nitrogen and the vacancy being bonded to one another. Obviously, a nitrogen can't be bonded to nothing. But conceptually, it's not crazy because there is electron density shared between the two sites. So the field of physics and biology have really gained some appreciation for this defect pair as a really transformational tool in both biology and physics. So biologists have found that, in particular, diamond nanoparticles can be used as very robust fluorescent sensors in vivo. So you can kind of put 4 nanometer nanodiamonds in cells and organisms, and the optical transition, the kind of fluorescence, like in the vanadium picture, can be used to do chemical sensing. And then physicists, on the other hand, have made tremendous progress in understanding and controlling the electronic properties of single impurities. So instead of having maybe a collection of impurities in their diamonds, they've tried to isolate just these single species, either chemically through synthesis or optically just through how they detect and excite the system. This nitrogen vacancy defect is magnetic, as we just described, and it can show kind of quantum behavior up to room temperature, which is kind of the thing that makes it really exciting. It has very long coherence times at appreciable temperatures. So let's talk a little bit about quantum communication. So quantum communication is designed to transfer encoded information between distant locations through some quantum communication network. And it's designed to enable two big things. The first is full security. So quantum communication applications are aimed to ensure complete protection when information is transferred between locations. The most popular method to do this is called quantum key distribution, and it involves sort of assigning different people a confidential shared key for accessing data. And these kind of quantum encryption protocols are more robust than the best classical encryption. So the best classical encryption today is RSA, and people appreciate that this is going to be vulnerable once even the most basic quantum computers come online. So that's why kind of people have worked really hard to get quantum key distribution functioning beforehand. There's a kind of a famous quote about this field that says, we know mathematically that they never offer the same kind of security as quantum key distribution, meaning classical encryption methods. And so this is something that a lot of folks have embraced. And then the second thing that quantum communication is intended to enable is enhanced computing power. So there's this interesting connection between quantum computing, which again is going to be the focus of a lot of our class, and this idea of quantum communication. So in terms of enhanced computing power, there's sort of two important types of quantum processing that we can consider. There's parallel processing, where multiple processors are connected and simultaneously execute different calculations broken down from a larger problem. So in a silly kind of classical example, we can say that if we wanted to calculate the route between distance between 15 different cities, a classical computer would just do them one at a time. Whereas in parallel quantum processing, the distance between each city would be calculated simultaneously and then added. And so the other type of computing that we think about in quantum communication is blind quantum computing. And here, quantum communication is intended to provide secure access to some remote, large-scale quantum computers in the cloud. And so the remote computers don't have full access to the information that they're processing, and that is what would increase security of doing computation like that. And it also is what will allow us to do sort of remote quantum computation from our home computers and still be safe. So the ultimate goal of quantum communication is to establish something called the quantum internet. For quantum internet, most areas will rely on fiber optic networks, which are reliable, but somewhat expensive. And we have a lot of existing fiber optic infrastructure that can be leveraged, which is nice. And the transmission of quantum information along short distances, less than 500 meters, is already possible via these fiber optic networks. So short-range communication is already possible via fiber optics. Transmission over longer distances won't be feasible until researchers in the field have figured out how to create fully functional quantum repeaters, and you can see those kind of in this schematic diagram. And those are devices that amplify signals and reduce the amount of information lost during this transmission process. And it's expected that those kinds of quantum repeaters might be available over the next decade. And for some long-distance communication, quantum satellites are being considered. So if you want to transmit information across an ocean, for example, that would be the way to do it. But those aren't going to be suitable for all locations, including places with extreme weather, for example. But this kind of creation of satellite networks and the related ground infrastructure needed for quantum communication also kind of presents a lot of challenges that current researchers are thinking a lot about. So quantum internet is a future. But some aspects of quantum communication is already happening, and this kind of small quantum networks over short distances already exists. And a key to this kind of short-range quantum communication is something called quantum key distribution. But this is kind of something that's really at the heart of this technology, and it's something that, like I said, already exists in many mid-scale or has already been made available to many mid-scale companies. So we'll talk about that right at the beginning of class on Wednesday.